passengers, this is your pilot speaking. We will be taking off from UTSC shortly, on our way to Lake Nasser, Africa. Now, if you thought Africa was only made up of hyenas, lions, and elephants, then you are sadly mistaken. Africa is also home to some of the world's largest man-made lakes in the world, one of them being Lake Nasser. Flux capacitors on, thrusters at full blast, and we're off. Lake Nasser begins in northern Sudan, where it extends approximately 500 kilometers through southern Egypt until it reaches the Aswan High Dam. The lake has an average width of 12 kilometers, an average depth of 25.2 meters, but can be as deep as 180 meters, giving it a surface area of approximately 5,000 to 6,000 kilometers square, and a volume of 132 cubic kilometers, depending on the season, water flow, and water released by the dam, of course. Construction on the Aswan High Dam itself began in 1960 and was completed in 1968 after backing from the Soviet Union. Original backing was supposed to come from Britain, the US, and the World Bank, but this fell through before the project could gain traction. The thinnest dam consists of rock, metal, and cement, measuring 110 meters high, 3,380 meters long, and 980 meters wide. The dam was built with 180 sluice gates to control flow and 12 turbines to produce energy for about half of Egypt's power needs. The creation of the dam was met with some controversy, as most dams are. The dam changed the flow of the Nile River, affecting irrigation and biotic life in the area. Also, the newly created reservoir submerged several historical sites and led to the relocation of approximately 100,000 inhabitants. For dam operation itself, the lake is divided into 6 zones. The first, called the Dead Storage Zone, has an elevation of 147 meters and is used for sediment collection during the flood period. Within this zone, no flow is to be released regardless of downstream requirements. The next zone, the Live Storage Zone, operates to meet downstream requirements without exceeding Egypt's annual quota, which is 55.5 billion cubic meters. The Live Storage Zone has an elevation of 147 to 175 meters. The final zones, called the Flood Buffer Zone and the Flood Control Zone, elevated at 175 to 178 meters and 178 to 183 meters respectively, are used for flood control. Any flow that exceeds the buffer zone into the control zone has to be spilled. Now how about a little lake knowledge? Okay. Lake Nasser is one of the world's largest man-made reservoir lakes. It is a warm, subtropical, monomictic lake, overturning annually during the winter, where mixing improves the water quality. The Nile floods once a year, in August, originating from the Ethiopian highlands, and if the Nile floods, so does Lake Nasser. Year-round, Lake Nasser receives roughly 84 billion cubic meters of water inflow from the Nile River, which is a lot. Being a warm, monomictic lake, Lake Nasser stays quite warm. Lake Nasser varies between 18.3 degrees Celsius in the winter and 31 degrees Celsius in the summer, with an average temperature of 25.6 degrees Celsius year-round. Now I take it you're all students, and all students know that cold water is able to hold more dissolved oxygen than warm water is. This is evident in Lake Nasser, but not in an extreme way. Lake Nasser averages 7.95 milligrams per liter of dissolved oxygen, safely above the typical required limit for most fish to grow and breed, and is about 75% saturated with dissolved oxygen during the summer and 114% saturated during the winter. Now I'm going to hit you with some numbers, so try to stay with me. Lake Nasser is quite rich in dissolved nutrients. It's limited by phosphorus, which is very typical for most lakes. Its phosphorus levels range between 0.010 and 0.105 milligrams per liter, with a peak during the summer. Its nitrate levels range between 0.159 and 0.378 milligrams per liter. Overall, the lake is slightly basic, ranging between a pH of 7.74 and 8.73, peaking during the spring. The lake ranges from a relatively clear lake with a turbidity of 3.68 NTU, or nepherometric turbidity units, upstream in the spring, to a somewhat cloudy lake downstream in the summer with a turbidity of 54.77 NTU. Turbidity within the lake is caused by 2 main factors: silt coming from riverine origin in the upstream area, and suspended organic material coming from the lake itself in the downstream area.
Conductivity in the lake ranged between 221 and 256 ms per centimeter, with an annual average of 239 ms per centimeter. Values increased downstream with a maximum peak in autumn. Oh, and by the way, ms stands for microsamens, or dissolved ions in the water. The levels of chlorophyll A increased during the summer to 21.9 milligrams per meter, and autumn 17 milligrams per meter, while it decreased in the spring to 9.3 milligrams per meter. The highest values were measured upstream and decreased gradually downstream. In Lake Nasser, nano and picoplankton represented more than 63% of the total chlorophyll A levels. Now, why does all this matter? Well, I'll tell you. First of all, you have to remember that lower conductivity lakes yield greater densities of typical plankton species. And Lake Nasser is a low conductivity lake that has had a very stable zooplankton composition, remaining very similar to what it was in the 19th century. The lowest standing zooplankton stocks coincided with the lowest chlorophyll A during the spring, which makes sense since the majority of chlorophyll A is phytoplankton, and zooplankton eat phytoplankton. The density of zooplankton started to increase towards the upstream. This was coincided with rich nitrate and phosphate levels. At the downstream, the fish predation increases due to high transparency, leading to decrease in zooplankton density. Remember how I said turbidity, or water clarity, was lowest upstream? Zooplankton density also changes with the oscillation of the lake water level. Zooplankton stock was highest at lower water level in comparison with the highest level. This is directly related to fish production. High water levels increase shallow water areas, increasing the spawning areas for fish. High fish production lead to high predation on zooplankton, and thus decreased zooplankton stock when water levels are high in the lake. Lake Nasser is a freshwater lake, so it consists mostly of freshwater fish. The most dominant fish in the lake is tilapia, accounting for roughly 96% of the fish catch. Other more dominant fish include Nile perch, which is a prize catch and the greatest attraction for sport fishermen, catfish, and mormyrids. Lake Nasser also consists of some saltwater fish. The two most dominant saltwater fish in Lake Nasser are cyprinids and characins. In comparison, freshwater fish consist of about 90% of the total lake catch, while saltwater fish are the remaining 10%. But this wasn't always the case. During 1966 to 1970, saltwater fish made up about 40 to 57% of the total catch in Lake Nasser. This decrease in saltwater fish is directly related to the construction of the Aswan High Dam. The dam created a barrier between the saltwater outlet of the Mediterranean Sea and Lake Nasser, making it nearly impossible for saltwater fish to enter Lake Nasser. Two typical problems that reservoir lakes face are greater evaporation rates and sediment buildup. Evaporation has been measured at 0.86 billion cubic meters per month from Lake Nasser. Evaporation levels can be combated through dam operation. Allowing for a more constant, smaller spill rather than a few large spills can increase the flow of the lake and reduce evaporation. This can be done by allowing certain sluice gates to remain open more often. Sediment buildup has been ever increasing over the years since the construction of the Aswan High Dam. Water and sediment discharge into the Nile vary heavily year-round. Minimum discharge occurs in May, slowly increases during June and July, rapidly increasing in August and reaching its peak in early September. Discharges drop rapidly through October and November, and then the decrease slows until May. Increased lake volume increases cross-section width, and because cross-section width implies an increase in the flow area and consequently a decrease in the flow velocity and sediment carrying capacity, the bulk of the deposited sediment concentrations in the upstream part of Lake Nasser. Smaller particles now account for a greater percentage of downstream suspended particles due to the decrease in flow velocity, leading to the deposition of larger particles upstream. This means delta formation is occurring upstream due to sediment buildup caused by decreased flow velocity. Based on past, current, and future predicted sediment deposition, the dead storage zone of the lake is calculated to have approximately a 310-year lifespan. Cause this is Africa. This time for Africa.